All right. It's a pleasure to welcome our second speaker this morning, Professor Jelena Grbic from University of Southampton, and she'll talk about Steenrod operations on polyhedral products.
Thank you, Taras. And thank you to the organizers for giving me the opportunity to come here, to enjoy and have fun, and also to give a talk. So yes, I'll be talking today. It's a very easy kind of talk on Steenrod operations on polyhedral products. And the hardest part is to write down all the surnames of my collaborators. So this was part of Women in Topology Network series. So hence so many quotas. So Sanjana, Michelle, Milica, Evgenia, and Sarah, together with me, we're really learning about polyhedral products. None of them ever working in toric topology or associated areas. So it was lots of fun. Okay, so as I said, I'll keep it easy today. And so the idea is, what can we say about any cohomological operations on polyhedral products or their kind of similar or related spaces? And we started with the Steenrod operations and haven't moved further away from them. So if anyone wants to study other cohomological operations, and I know Stephen was talking about certain operations on Stephen Amelet on polyhedral products earlier during this program. Okay, so I know some of us were talking every day, at least 20 times mentioning polyhedral products, but I feel since it's Monday and it's early morning, I can remind us what the definition is. So let's start with a simplicial complex K on M vertices. And so this is one M. And then we consider M pointed topological pairs. So okay, and to them we associate the polyhedral product as a subspace. Oh, when I put under bars, so this denotes this M tuple of topological pairs here. As a subspace of the Cartesian product of all these xi's that is governed by the shape of the simplicial complex K, where these subspaces, as I said, are glue along K, and subspaces are given such that those coordinates that are not labeled by sigma are allowed just to stay within AI, and those that are labeled by sigma can move throughout whole Xi. Okay, so our main arbiters will be for today the Davis-Januszkiewicz space, which we can write as a polyhedral product of CP infinity and a point where all M pairs are identified with this pair to K, and the moment angle complex D2 S1 to the K. Okay, So these are the guys that we will look at coming from polyhedral products. And as I said, like we wanted to study some cohomological operations. And so the cohomological operations are natural transformations of the associated cohomology functors. And the first one that actually we know already in this setup is looking at the cup product squaring. And this is, yeah, so okay, let me say, this we start with a N cohomology, R is some commutative ring, doesn't matter. And we associate to it, so we start with a class, and we associate to it the cup product, so, or cup square, yeah. So that's essentially how Steenrod squares were introduced. So you have the cup product squaring that induces a family of cohomological operations, and they are unstable operations because obviously if we suspend X, we kill all cup products. So this becomes trivial. So Steenrod then defined his operations. So Steenrod squares by really looking to have some kind of squares, but wanting them to be stable rather than unstable. So he defined Steenrod squares by, say, I square. So it takes the nth class in the mode 2 cohomology of a space and associates a class of degree n plus I. Okay. So these are primitive cohomological, stable cohomological operations. And you can construct them geometrically, or you can approach them axiomatically. So what you can see is that these squares, they generate connected graded algebra, where these SQIs, ith operation, I squares are generators, but this algebra is subject to the Adam relations. And as I say, if you were to define them axiomatically, you could say that they're such that square 0 is the identity, and we have this instability condition telling us that if you start if you start with n class, all cohomologies will be with Z2 coefficients. I'll stop writing the coefficients. And you apply to it n square. It means you will land in 2n of x. That this is just the cup product squaring. So SQn x, so the degree of x is n. Then this is just x f. And if if you take square d, say where d is greater than the degree of x, in this case n, then the Steenrod is acting trivially on that element. Okay, and then I mean not write all the axioms, but just saying that that interplay of the Steenrod squares with the cup product is given by the Cartan formula. Okay, or you can, because I'm going to use it, I'll define it here. You could say the same thing by saying that the total square that is given as the sum of all squares is what it is. It's an algebra map. It's a multiplicative map. Okay. So this is what we want to study for certain polyhedral products, namely how this Steenrod algebra is acting on certain polyhedral products. So the easiest thing to start with as a warm-up is to look at the Davis-Januszkiewicz spaces. So a polyhedral product of CP infinity point to the power k. Okay, so we know that the cohomology of Davis-Januszkiewicz space for any R, ring R, but I'll SSL, since I want to study for this talk, just talk about mod P, Steenrod operations, I'll take Z2, is the Stanley-Rising ring of K, namely that is a polynomial algebra on m variables, and then we quotient it out by the Stanley-Riser ideal. So here we are assuming that all xi's, I usually write all my life vi's. I don't know why I switch for this talk for some reason to xi's. Yeah, my notes are v, doesn't matter. Xi is equal to 2. And now let me just recall that the Stanley-Riser ideal is the ideal generated with the square-free monomials labeled by sigma, where sigma is not a phase of K. Okay. So yeah, if sigma is it's a subset of m vertices, so it's say I1 to I1 to IL, then you take a square-free monomials on those axes that are labeled by sigma. Okay, so so one can ask, okay, how does the Steenrod algebra act here? And so what we have to do, this is an algebra isomorphism, sorry, this is the definition. Well, here it's easy. So all what we have to do is to look at this algebraic object and put the right action of the Steenrod algebra. I mean, on this part, you can put many different actions, and obviously because we want to show that this isomorphism is isomorphism of A algebras, A Steenrod algebras, then natural thing to do is to recall that this is coming from the cohomology of CP infinity and just use those Steenrod squares. So in other words, the total square of xi is xi plus xi squared. Okay, so once you have that, then obviously you can see that this ideal is closed under the action of the Steenrod, because of what it does when you apply squares to monomials like that they just raise the powers. So obviously, if they were labeled by something that is not a simplex in K, what you get will be divisible by this guy again. So hence it's sitting in the ideal. Okay, and now so I'm showing this trivial example just because I don't know to do anything more complicated, as I will illustrate later. So so once you have this algebra, once you have the Steenrod algebra acting on this algebra side, then you have to show that this is isomorphic to the geometry. So obviously here, what we're going to do, we'll look at Davis-Januszkiewicz space and recall that this is a polyhedral product, namely sits nicely into the product of CP infinities, copies, and you look at CP infinity as a CW complex and say, well, okay, it's built, all the cells are such that in each even degree we have only one cell. Then you take the product and induce product CW structure on it. And then you see that this inclusion of the Davis-Januszkiewicz space into CP infinity is nice. So namely, all the stuff that we know how CP infinity acts, how the Steenrod algebra acts on CP infinity will be kind of close on the Davis-Januszkiewicz spaces. And then obviously you show that that gives you that this isomorphism is isomorphism over the Steenrod algebra. Okay. Sorry. So, and now you can play the game further. So like how important was that this is CP infinity? Well, not much. So what you can do, you can consider any polyhedral product X base point to the K. And if Xi's are nice in the sense that if they satisfy the strong Kenneth formula, namely if we take that cohomology, okay, of X1 tensor cohomology SAM is isomorphic to the cohomology of X1 plus M, then BBCG. So Tony, Martin, Fred, and Sam tell us that the cohomology of these, in a way, generalized Davis-Januszkiewicz space has an analogous form of the Stanley-Reisner ring, namely, I'll keep here coefficients Z2, but it works for any R under which we have this isomorphism. Yeah. So, sorry, what do I have? Yeah, so what's here? We have the polynomial algebra on X1 to Xm, but this is nothing else but the cohomology of CP infinity tensor by itself m times. So, okay, so you have cohomology of X1 tensor and you portion out with the Stanley-Reisner ideal or generalization of that corresponding to X1 to Xm. And well, let me not write that explicitly, but it really generalizes this. So before we had all axes, oh, maybe it's easy actually to write and then I don't have to worry. let me write here. Board organization, terrible, but okay, survive. X1 to xm are square-free monomials. I don't know, P, such that each this xij belongs to the cohomology of xij. And this simplex determined by these indices, I1 to P, oops, is not a simplex, okay. Okay, so here, again, you can determine explicitly the action of the Steenrod squares, namely, each cohomology of topological space has the action of the Steenrod squares. And if you recall that there is co-multiplications in among Steenrod squares that will induce Steenrod action on this tensor product. And then from there, you again play the same game. You show that the ideal is invariant under the Steenrod action, and you determine the action of the Steenrod squares on this polyhedral product in terms of the Steenrod products on each individual space xi. Okay. Yes.
Do you really have to show this invariance of this ideal? I mean, shouldn't that drop out? Shouldn't that be necessarily the case? Because somehow the map, I guess the map from the cohomology of the Cartesian product to the cohomology of the polyhedral product that comes from the inclusion is surjective.
I'm saying much more trivial thing than you are talking about.
It's
I'm
sort
just
of
saying
automatic. It's just automatic that this ideal is stable.
Yeah. That this is an isomorphism is an automatic. All what I want to say first is that I want to define here. I can define various Steenrod algebra.
But you don't need. I mean, the first map is. You know how the map above interacts with the Steenrod squares by the Cartan formula, right? From the tensor product to the Cartesian product.
Yeah, that's what I said. That's how I define on the tensor. And then I say, why can I quotient it out? Why can I define
just by
thing?
natural? I mean, there's nothing to define. It's just the Cartan formula, and then it's natural, and then because it comes from a map of spaces, I think it's necessary.
Proof is trivial. I'm not saying that it's difficult. I'm just saying you have to check that this ideal is closed. Yeah, but. The proof is super easy. I'm just saying, let me tell you what my problem is with the moment angle complex, and then you'll see why I kind of try to tell people, yes, there are lots of different Steenrod squares that you can define here. This is the easiest way and most natural to define one that will then match this kind of geometric side. Yeah. Okay. So obviously then, as an example, you get the Steenrod action on the real moment angle complex. What do we have? Infinity. So, okay. Well, again, so this is Stanley rising ring. Oh, just XM, in this case then O in degree 1, and obviously the formula depends only on the Steenrod action acting on RP infinity. So if you take xi, it's xi plus xi square. This is the total square. Yeah. Quotient portion, you're absolutely right. Thank you. So yeah, so if you want to move forward, and think, what can we say about the moment angle complex? So things are kind of, as I say, here everything was really trivial. I mean, you just have a nice presentation of the cohomology of David Januszkiewicz space, and you're using that to just state the things, as you really need to work hard on that. However, here we don't have an explicit presentation, but we know that the cohomology of ZK is the isomorphic to the Tor over the polynomial ring. Oops. Or the Stanley-Reisen ring. So what do I have? Z2K and Z2. And I don't know how to put the Steenrod algebra action on this guy to be able to then see what's the Steenrod. And I still don't know. After so many months of thinking, one natural thing would be maybe take a resolution, see what it goes there. But the resolution, that's when you remember all these things that you learn as a PhD student and learn them too inaccurately because this is a commutative. If you were to put the Steenrod algebra on the resolution, on the Koszul resolution, sorry, you end up with a trivial Steenrod algebra, and that definitely is not the one that would correspond to here. Yes, Tony, sorry. I look at that and I try to mimic that on this side, and I couldn't find that matches. So yeah, so that's for people who want to play with this. This is one thing to do. So what kind of Steenrod operations can we put on the Tor so that they correspond to the Steenrod action on the moment angle complex? Okay, so for me, that was a dead end for a long time and still is. But as I said, at least I recall some basic things about Steenrod algebra that I incorrectly learned or remembered from my youth. So, well, but then again, Tony, Martin, Fred, and Sam come to help. And they tell us that if you suspend the moment angle complex, then it breaks nicely in terms of full subcomplexes. So, okay, so this is wedge of, oh, I probably need more suspensions. Do I not know this by now? Suspension. Oh, why do I have some? Oh, sorry. One sum is sigma is sometimes sum and sometimes suspension. At this point, I need it to be a suspension. So I have wedge of suspensions of J plus 2 of the full subcomplex on the set J. And J is, what do I have? J is not in K. Okay, so now one can say, well, okay, now we are done because we know that Steenrod squares are stable operations. So now we can determine the Steenrod actions on ZK with respect to the, in terms of the Steenrod actions on the full subcomplexes. Obviously, this induces an isomorphism in cohomology. What I have J plus 1 of the cohomology of Kj. And now, well, yes, this is kind of abstractly, we know everything, but can we now say something about the Steenrod action on ZK. I mean, apart from saying abstractly, yes, whatever Steenrod square we have in the cohomology of these full subcomplexes, it will rise to the Steenrod algebras here. Steenrod action on the moment angle complex. Okay, so first to notice, again, these are all very trivial observations, but fun nevertheless, I think, is that if the dimension of the simplicial complex K is, for example, D, then all squares where n is greater than half D will be trivial, because obviously this is a geometrical dimension of simplicial complex, yeah, no, not cohomological. Since K is of dimension D, then all full subcomplexes will be of dimension less than D as well, or equal to D. Okay, and in particular, if K is a graph, then there are no non-trivial Steenrod operations. On ZK. Okay. And I mean, this is just, as I said, a simple corollary, but we know much more about the homotopy type of moment angle complexes that are associated to a graph. So we talked about that in this program. So Stephen and Taras were mentioning, you know, if you have an n-gon, then ZK is a connected sum of a product of two spheres, or, you know, you can, if you have 2 points, it's a sphere, and so on and so forth. Okay. So playing this type of game, we can look at a simplicial complex K that is a triangulation of RP2. RP2. And now, so look at RP2 and take its triangulation on 6 vertices. So I'll denote that as P26. So that's something like this. Let's see. Okay, so if I put 1, 2, 3, and then 4, 5, 6, 4, 5, 6, this identification, as we usually put for the RP2 model. So now you can see, first of all, ZK is homotopy equivalent. So this BBCG decomposition, this suspense, and this is some wedges of spheres. We know the number C alpha, say. And then wedge of what? Suspension 7 of RP2. So Taras, Stephen, G. Wu, and I showed that this, in this case, ZK splits unstably. And obviously here you have the Steenrod action acting here. So if you take x in degree, what, 8, and y in degree 9, this is connected by square 1. And obviously you can see that here by taking in K, or in the cohomology of K, you will have x in degree 1 and y in degree 2, and they are connected by square 1. Okay, so that tells us something. So this is a minimal model or minimal, yeah, model of RP2, and we can see that whenever this complex is a full subcomplex of K, then there is a non-trivial square one in ZK. But also that gives you a nice kind of statement or observation that on all classes below or equal degree 7, you can't have non-trivial square one. So square one acts trivially on classes of degree is equal to 7, and this is an optimal bound because obviously when it's a when you in degree 8, yeah, we have a non-trivial square one. Okay, so what we I'm 1/3 through my lecture thinking. Okay, so the way we proved that, we actually, I was planning to talk about that, but now there is no time. We developed a formula for square n, for any action of square n on a cochain of simplicial complexes. So it's this kind of computer scientists, they're already, or topologists, they already developed, there exist algorithms. However, we developed a slightly faster one, and we use that just for fun to prove this. And also as a consequence, we got that this is a minimal model. Because, you know, if you're looking through the literature, there is no minimal model for RP2. There is no explicit kind of reference. Why would this be a minimal model of RP2? Okay. Yes?
Jelena, up there where you've got the cohomology of ZK splits up like that.
Yep.
Well, even in the general case, if you have the stable splitting, you can put a ring structure on the right-hand side. That
Yes.
ring structure is isomorphic as rings
Yeah.
to the ZK. So it's a sort of interesting. I
Yes.
don't know if it follows.
I want.
I don't know if it follows, but if you use the star product or whatever to define Steenrod operations on the right, that they would be isomorphic rings over the Steenrod output. That's worth asking.
That's, yeah, that's right. Star product could be used. So here, what is again, it's just an observation, is that Steenrod actions here are how to say, they sit inside each summons, so they don't mix summons, where the cup product mixes the summons. So if you want to have non-trivial cup product, you have to take one Kj and another Ki, where J and I are disjoint. So in that way, where Steenrod is acting really just inside each summon, so it's not mixing. So that's one way to show that there are no cup squares in ZK. Yeah. But yes, on a cochain, but yeah, that's another approach to look whether one can explicitly define Steenrod algebra on using the star product. Yeah. Yes.
You talked about a minimal model for RP2. Did you mean a minimal triangulation?
Triangulation, sorry, it's simplicial complex.
That's not known? What a minimal?
No, so like I try to find non-trivial reference to this statement. and it is known, but it's I couldn't find, as I say, a non-trivial statement that implies that this is the minimal complex. Yeah. So yes, it is. From here also we can see that is minimal because it minimal triangulation of RP2. Yes. Because if there was a smaller one on few by minimal, I mean on a small number of vertices. So now a question to topologies is, okay, so for square one, we know we need at least 6 vertices to define a simplicial complex that C square one. What about higher squares? Namely, if how many vertices? So this is, if I have square I, what is the minimal number of vertices of a simplicial complex K such that square one I acts trivially, non-trivially, sorry, on that simplicial complex. And then if we have that, then obviously you can show that SQI would act trivially. So this is kind of corollary on classes of degree what M I plus I in ZK. But what is the smallest simplicial complex in which we can say C squared 2? I don't know that. So, but I was hoping that maybe there's so many good topologies and homotopy theories here that someone could tell me which simplicial complex to look, say, to realize square 2. Realize non-trivial action of square 2. Okay, so Tony was mentioning this week that construction of polyhedral joint is underutilized in our subject. So the definition is same as here, except if I want join, I put join here, and I put join here, and this is also kind of join. So the advantage of looking at a join is that if you now take a sequence of simplicial pairs, say K, then this polyhedral joint product will be also simplicial complex. So what do we want? Now we saw from this stable decomposition that if we know how the Steenrod acts on simplicial complexes, then we know how it acts on the moment angle complex. So now this full subcomplex, when you have K, you really can't you can't classify in general what will be full subcomplexes. Full subcomplexes can be whatever you want when you, in general, yeah. So in other words, they are not determined by K, yeah. So so one interesting simplicial complex is this one coming from the polyhedral joint, and so there are. This is a general one, and then we can look at special families. Namely, if I, for this sequence of Ks, if I take simplex, a full complex, yeah, and then I take the boundary of that simplex, then we recover a a construction by BBCG, and they call that simplicial wedge and denote by, say, L1 to Lm. And then Anthony Eisenberg, so he generalized this into what he calls simplicial composition. And denotes by K of L1 to Lm. And then Taras and Semyonov had another. So this you could almost think as an analog of the moment angle complex. You have contractible space disk, and then, okay, it's not S1, that's here, but this is a subcomplex. And then kind of the analog of Davis-Yaroshkevich space would be that to take some complex K here and the empty set. As I said, Taras and Semyonov called it substitution complex. And denote by Q1 to Kn. Okay, so in general, if you're looking at that simplicial composition, then neither K nor L1 to Lm are full subcomplexes. So you would think, so what I want to, if possible, I know how Steenrod acts on K, and I know how the Steenrod acts on L. Can I say how the Steenrod acts on the whole guy here? So what we did, we showed that actually this is homotopy equivalent to K join L1 join Lm. And although, as I said, Li and Lm to Lm and K are not full subcomplexes, you still can say that the Steenrod action on K, L1, and Lm will rise to the Steenrod action on Zk, because K is a full subcomplex of itself. Here things are nicer from the perspective of moment angle complex, in a sense that all these K, K1, and Km, they're all full subcomplexes of this substitution complex. But I'll close, so therefore the Steenrod action on them will rise to the Steenrod action on Zk. But maybe again, as an open thing for people to think about and use maybe in the future, I'll give you the deconstruction, not just a construction of this substitution complex that I find very interesting in a sense that it can be used in homotopy theory or polyhedral products a lot. So we are looking at a substitution complex K1 to Km. So remember that that's a joint product where we take a K1 to Km, and a subcomplex is just the empty set. And I'll assume, as always, that K is on M and Ki is on Ni vertices. And if this construction in a way can be iterated. So if I denote by K naught K, and K1 is now substitution of just K1 into the, instead of first vertex, sorry, wrong brackets this. And then I keep dots will be one vertex complex or can call it just a point or a vertex. So then K1 is obviously on N1 plus M minus 1 vertices, because we kept these M minus 1 vertices, and instead of the first vertex, we substituted K1 that is on N1 vertices. Okay, and then K2 will be K1, then you have these dots, vertices, and 1, and you substitute instead of the second vertex in K, you put K2, and the rest you keep as it was. So this is a complex now on N1 plus N2 plus M minus 2 vertices. Okay, and then finish by saying that Km, as you can now guess, just this iteration, you come to Km minus first stage and complex, and into it you substitute, this is all dots, the last complex Km. And obviously these are how many vertices you have, well, the sum of ni's when I goes from 1 to M minus 1. Okay, then I'll stop here, then we can say that K, the substitution complex K1 to Km is homotopy equivalent to K wedge link in K naught or K of V1 join K1, and then you have wedge all the way to the last sum, and I'll write it here. That's a link in Km minus 1 of Vm join Km. Okay. So I think this is a really nice decomposition of this substitution complexes, and as I said, like I was using it to determine some Whitehead products and things like that in the homotopy theory of polyhedral products. I'll stop here. Thank you.
Thank you.